Dr. Richard Feynman is an award-winning physicist who taught theoretical physics at the California Institute of Technology for some years. During this time, Dr. Feynman took part in what is referred to as the Messenger Lecture series. Feynman's Messenger Lectures describe the characteristics of physical law piece by piece. The intent of each episode is to explain almost enigmatic concepts in a simple way, using analogies that even those with an untrained mind will be able to apprehend. Today we will be discussing Episode 4, Symmetry in Physical Law. When we describe symmetry in nature, we think of things that are the same on all sides. Things like snowflakes, butterflies, many flowers, and even the shapes of planets, spheres. However, we must use a different definition when discussing symmetry in physical laws. A thing is symmetrical if there is something that can be done to it so that after you're done doing it, it'll look the same as it did before. We can make changes to things that have no effects on physical laws, and here are a few examples. Number 1. A translation in space. When moving an apparatus from one location to another, it will proceed to work the same way if the same change is made to every condition that may have had an effect on the object. Picture two magnetic balls. As Coulomb's law states, the electric force is measured to be kq1 q2 divided by r squared. The electric force will be the same as long as the distance r between the two spheres is maintained. Thus, the apparatus will function the same way whether the balls are here or here, as long as they are not separated any further or brought closer together. The equation does not take into account the apparatus's distance from the nearest galaxy or the distance from the Earth. However, in other instances we would have to take that into consideration, like how gravity is affected by the distance between two massive objects. When you are on the Earth's surface, gravity is measured as 9.81 meters per second squared, but if you were an astronaut floating in space, that is spatial translation, the force of gravity impressed on you by the Earth would differ by your distance from the Earth's surface. Gm divided by r squared. All conditions that affect an apparatus must change too, in order to maintain symmetry of the physical laws in a spatial translation. Number 2. A translation in time. A translation in time also has no effect on the physical laws of the known. If velocity is maintained, a delay in time causes no effect on the apparatus itself. But this is only possible if you neglect the expansion of the universe. Since we know the universe is continually expanding over time, and we don't know how or why, we don't know 100% that the functionality of the apparatus stays the same with a translation in time, as this fact could have some sort of effect and we would not know what that is. If you woke up in the future, in a fantasy world similar to ours, only immortality was constructed, and you did not know what time it was, you could tell the year by measuring the distance between the galaxies. But the effect of expansion cannot be taken into account as we know so little about the start of the universe and about the future. In reference to momentum, as far as we know, life is not deterministic. Symmetry and translation in time exist, but it is limited only to what we know about the universe. Number 3. A rotational translation. A rotational translation of an apparatus will cause no effect on the physical laws. Take, for example, you kicked a soccer ball and it accelerated as a result of the force impressed on it. Now, consider someone else kicking the same ball from your previous position with the same exact force, except you are watching from a different perspective. What do you think would happen? Correct. The ball would move the same way it did if you were to kick it. That is an example of a fixed rotation where the physical laws go unaffected. Both the observer and the kicker's x and y coordinates could be different yet still true and accurate, even the same when transformed. But wait, imagine a grandfather clock rotated 180 degrees sideways. The pendulum would stick to the side of the clock as gravity would be acting on it and forcing it to go towards the center of the Earth. However, if you rotate the Earth along with it, the pendulum will move regularly. Thus, there is symmetry in the physical laws of rotational translations too, as long as everything that affects the apparatus is maintained. Number 4. Uniform velocity in a straight line. Uniform velocity in a straight line has no effect on the physical laws, as they appear to be the same for the person who is moving, as long as everything else is moving along with them in uniform velocity in a straight line. And they would not be able to tell who is moving and who is stationary. When we discuss symmetry in physical laws, we are addressing taking one piece of the universe and moving it over, whilst making sure about enough conditions that it still won't make a difference on the apparatus. Even if we add a constant speed, the laws of physics will go unchanged. Imagine an astronaut in a spaceship shines a ray of light and a stationary observer is looking at the same ray of light. You would assume that the speed of light moves at 300 million meters per second minus the velocity of the ship relative to the moving observer and 300 million meters per second plus the velocity of the ship for the stationary observer. But, as physics always proves that everything is not what it seems, this would be incorrect. Einstein's second postulate of special relativity is that the speed of light is constant, independent of the relative motion of the source. This means that space and time must be altered to ensure all observers see the speed of light as a constant of 300 million meters per second. And this means that time moves slower for those who are moving. The two observers' sense of time and sense of space may not be the same, and they wouldn't even sense it, as everything, including their brains, are working at different rates. Einstein came to this conclusion after his thought experiment where he considered two lightning strikes at his train station. The stationary observer would view the lightning strikes to strike at equal time as they were an equal distance away from him, but the moving observer would say the one he was moving closer towards struck first. Both descriptions would still be true and accurate as the speed of light was maintained, except for the moving observer, it's in train meters per train seconds, and they just cannot agree on what now means. Now, take a solid gold brick, 100% pure gold. If you replace one of the gold atoms with a zinc atom, the brick will no longer be 100% pure gold and it will lose its value. However, if you replace one gold atom with the same type of atom, it will once again be 100% gold. See, there are some changes that can be made that do in fact have an effect on the physical laws. The first example of the wrong type of atom in physical laws was first discovered by Galileo Galilei, and it is a change of scale. If you were to build an apparatus and make it 10 billion times larger than it was before, using an enlarginator like Dr. Doofenshmirtz from Phineas and Ferb, well, like all Dr. Doofenshmirtz's ideas, the apparatus would fail as it would likely collapse on itself. Similar to the concern with larger ships out of water, it is highly likely for them to collapse on themselves, while for smaller ships, it's not as much of a possibility. Even if you were able to change the size of the Earth along with it, it still wouldn't work because the force of gravity due to the Earth on the object would be greater and it would once again collapse. It would be the same if you took an apparatus and instead made it 10 billion times smaller, but it would likely only be comprised of a number of atoms and cease to work. The idea that symmetry does not exist under a change in scale emerged from the idea that if you were to magnify an animal, its bones would not be thick enough to support its mass, and you would have to magnify its bones proportionally for it to even have a chance at survival. Number 2. Spinning at an angular speed. Another change that affects physical laws is spinning at an angular speed. This is because the centrifugal force causes all items to push against the walls when something is rotating at a uniform angular velocity. By using a pendulum or a gyroscope, which is a device that measures angular velocity, we can even tell that the Earth is rotating. Now, let's discuss symmetry in reflection. Picture a clock. Now imagine building a clock that is the exact mirrored reflection of the original clock, simply a left clock and everything involved is turned around, like a pair of shoes, one left and one right. Would the clocks work the same, only mirrored versions of each other? Well, according to the laws of gravitation, a reflection would have no effect on gravity. According to the laws of electricity and magnetism, a reflection would have no effect on its functionality. According to the laws of any nuclear reactions, a reflection would have no effect. At first glance, symmetry would exist in physical laws for reflection. Physically and chemically, we cannot tell the difference between reflections. We cannot distinguish between left and right. We can only do this biologically. For example, there are some bacteria that will only eat molecules that are unreflected while leaving the reflected ones, despite them being comprised of the same exact particles and bonds. To further explain whether or not the laws of physics are the same right or left, consider this scenario. You are on the phone with a Martian that is an infinite distance from you at an unknown location, and you had devised a way of communicating between each other. How would you explain to him the location of your heart inside your body? You could say that it's located on the left, but how would you explain what left is? You could say that when we have a radioactive disintegration, the electron that comes out of the rifled gun spins to the left, and thus our hearts are located on the left side of our bodies. We can only distinguish left from right with a very weak principle. Nevertheless, we cannot say that symmetry exists in reflections, although the distinction is weak. For each of the rules of symmetry, there is a corresponding conservation law in quantum mechanics. Momentum is conserved in the symmetry in a translation in space. The symmetry in a translation in time means that energy is conserved. Rotational translations exemplify conservation of angular momentum. There is a profound relationship between conservation laws and symmetry laws that cannot be explained using classical physics, but they are still noteworthy. However, the conservation of parity has been proved wrong, or simply put, the principle that you can't distinguish right from left has been proved wrong. Nature is almost completely indistinguishable right from left, but with the single phenomenon that is beta decay, we come to see that there is a difference between right and left and that symmetry ceases to exist in this particular principle. As you continue to analyze symmetry in physical laws, more enigmatic problems are introduced, and so we come to the philosophical question of why almost everything in the laws of nature is so close to perfectly symmetrical. Perhaps it's because symmetry is analogous with beauty, and if we were 100% symmetrical or perfect, the Martians would be so jealous of us and we would never be able to make that phone call. Thanks for listening, and I hope you enjoyed.